Hello physics students. In this video we're going to talk about electric field again. But I want to remind you that in this unit we are concentrating mostly on the electrostatics of point charges, meaning dots of charge like a single proton or a single electron. And within this unit we're going to be learning four big ideas that are like the foundation for electric effects of charge. And those four ideas are force and electric field, two topics we've already talked about. But yet to come is electrical potential energy and electrostatic potential or voltage. So two more ideas. But today, like I said, we're going to continue on a little bit with electric field. So today's topic is going to be just conceptual. How to draw electric field line diagrams. How to graphically represent electric field around some charge configurations. Now if you remember, one way to draw electric field was with little arrows. So if you flip back in the notes to yesterday's video, you would see that around a proton we drew a bunch of arrows of equal length close to the proton, pointing outward. A little bit further out, we drew a whole nother set of arrows pointing directly outward that were all equal length but smaller than the first set of arrows. And then further out, we drew another set of arrows. And you see that that's a very tedious process. Today, we're going to see that there's a more efficient way to represent electric field graphically and get the same information across. The electric field line diagram. So I'll pause the video to allow you to copy this portion of the board down. Okay, so instead of drawing those arrows for a positive, what we do is we just draw one set of arrows beginning right on the positive and extending out to infinity. Well, not really. We just draw an arrowhead indicating these lines go out to infinity. And for a negative, like an electron, we draw the same diagram, but with the arrows coming in from infinity. Now, just some things I want to point out. I'll do it here. You don't want to be sloppy about this. Like some students go like this. All right? And they left gaps here. Start your arrow right on the charge and extend outward. Okay? And be as accurate, as precise, as neat as possible, okay? Because again, we're trying to get as much information in the diagram. If your diagram is sloppy, so is the information that it's presenting. So here are the principles related to these diagrams. The first thing is, just like before, the electric field lines come out of positives and go into negatives, as you see in the line above. The field lines never cross. No matter how you have charges around in a particular configuration, field lines never cross each other because these lines will represent the net electric field. And if two lines are crossing, at the point that they cross, how can you have one net electric field this way and another net electric field that way? That doesn't make sense. You might have one component that way, one that way, but there's only one net final electric field. So field lines can never cross because they're in the net electric field. And how do we tell some qualitative, meaning non-numerical information about the electric field? The field lines are closest together where the E net is the greatest. So if we look at these diagrams, we could see that out around here in this vicinity, the electric field is weaker than it is in this vicinity because the spacing is closer. So we know E is most intense, the greatest magnitude, the greatest value near the electron or near the proton. Okay, so that's how we tell the same information that we had with those arrow progressively out shorter length. Okay, so point charges. The next example is the dipole. Okay, so what happens if you have a positive next to a negative? Now, if I just have the field lines like this coming out of the positive and then going into the negative, like this line, if I continue it in this one, they're going to cross here, which can't happen. So what we do is we still have the electric field lines come out of the positive, go into the negative, but they have to curve on their way there. So I do the diagram as neatly as possible. So what I did is I had one field line coming straight out of the positive, straight into the negative, and then as I go around here, I just curve them gently and then curve them ever more as they get pulled into the negative. This field line would go like this, and rather than draw and take up the whole board, I kind of left it off. Same thing up here, but really this curves around. The only exception is this one and this one, which do not curve into the minus. But notice again how I tried my best to make all the field lines start very precisely right on the positive and then go all the way to the negative. I don't stop here. I don't do sloppy like this, right? I want to continue that all the way till it gets to the negative. You want to take your time and draw it neatly to show that you understand the principles of the electric field around here. Another warning I'll give you is that for something like this, it's easy to make the field lines cross. If, for example, when they're coming into the minus, you just kind of go in a hurry like this, and then you start making them come in at the same point like that. Technically, those lines are crossing, and you have multiple net electric fields at that point. So make sure there's a gap between all those field lines at the minus, okay? So you want to take your time. Don't just go really nice and slowly, and make sure there's spacings between all those field lines at both locations. So that's the dipole, two poles of opposite. Another possibility, another example is, well, instead of a positive next to a negative, what's the net electric field look like? Oh, I'm jumping ahead. Let me also now say, so suppose I put a positive here, I can tell that the positive right there would not accelerate directly away from the positive or towards the negative. It would feel a force right here in the direction of the electric field like that. If I put a minus here, for example, let's see, maybe I'll think of a minus right there. It would feel a force not with the electric field, but opposite the electric field. So ultimately, it tells you how charges will feel forces as a result of these fields. But again, just very crude, qualitative, non-numeric, non-specific information from these diagrams. Okay, so okay, let's move on to the next example. I'll pause the video here so you could jot down example 3. Okay, so go ahead and jot that down. Okay, so now these field lines have to come out of this positive and out of that positive. Again, we've got this problem where they're going to cross, right? If they just go like this. So what you do is you have to curve this away from this field line so that they don't cross. So they kind of, you could think of them as almost like repelling each other, although it's, you know, the field doesn't repel a field, but they just kind of have to curve away like that. Again, we get the same information that the field is most intense maybe in these vicinities and gets weaker as you go further out. And right here, it would actually be 0. We know that from even what we learned yesterday. Okay, so example 3, positive, positive. Let's move on to example 4. Misnumbered. Example 4 and example 5. Okay, example 4. Let me pause the video to allow you an opportunity to jot that down. Okay, so in this example, we've got two minuses next to each other. It's the same as this diagram. Instead of the arrows going out of the positive and extending to infinity, they came from infinity and go into the minuses. But we have that same pattern of curvature so that they don't overlap with each other. And once again, we could see E is greatest maybe around here and here, but it's weak here, and then it's weak further out. So again, that qualitative information. Okay, last example, example 5. This actually, we're jumping a little ahead because in this unit, we said that we were only looking at the electrostatics of point charges. later in further topics, we're going to look at what happens when you start smearing charges around onto objects that are, like squares or rectangles or spheres. So that's coming in future units. So we're just kind of jumping ahead a little information here. But parallel plates, what we mean by that is like two sheets of metal perhaps, or two sheets of plastic that are charged up. Maybe you rub this with fur or something like that. You make it negatively charged, and then you make this positively charged by the same number of coulombs. So maybe this is like -5 microcoulombs, and this is +5 microcoulombs, these sheets of plastic or whatnot. And we put them close together so they are parallel plates of charge, okay? But they're assumed to extend very far in either direction. So we'll talk more in future units about what that really means. But what happens is we've got one plate positive, the other one negative by the same amount. Notice I have 5 minus signs and 5 plus signs. And then what we have is the electric field coming out of the positive going into negative. Again, don't be sloppy and leave gaps. Make sure it starts precisely on the positive plate and ends precisely to the negative. And you're going to want equal spacing, because the reason why parallel plates are used in physics experiments is because they make a relatively constant electric field between them. And so even though you're here or in the middle, E is constant everywhere. And so the way we indicate that by this principle here is we've got to make the field lines equal spacing. And that indicates the field is constant. At the edges here, we have what are called edge effects. So this is not a constant electric field here anymore on the outside, but between it's relatively constant. So that's it for today, a nice short video. So again, we're just looking at a new qualitative way to sketch the patterns of electric field, which are, out of the positive into the negative, gives you just the concepts behind the electric field and the patterns of the field in these various charge arrangements. Okay, so that's it for today. I'll see you in the next physics video.